Hey, welcome to another video. So, in this video, I'm going to show you how to complete the square easily. Go, easily? Completing the square is not easy. Yeah, it can be a little tricky, but the way to make something easy in math is to understand it. And so what I'm going to do, I'm going to teach you why completing the square actually works. Because I can't afford for this to be a process for you. Something like, oh, you do this and this, and then you're good to go. I need you to understand what it is that it's doing. And the reason why it's important is because in this class, in like pre-calculus, intermediate algebra, we have other ways we can solve quadratics, like the quadratic formula. But what completing the square does is gives you a very powerful tool that you will be using later in math. Like in calculus 2, we use trigonometric substitution to solve some integrals, and you have to complete the square on some of those problems. So I'm going to show you why it works, how it works, and it's going to seem a lot easier when we're done. So we're going to solve some quadratics. We have one up here that's factorable. We'll talk about them in a minute. And then we have some ones that aren't. So there's two principles I need you to understand before we get started. The first one is this. What we're going to be doing, how to make completing the square easy, is to understand that what it really is taking something, the quadratic, forcing it to factor as a perfect square so that you can use the square root method to solve it. So we're looking at a quadratic, we're saying that doesn't factor. Otherwise, we wouldn't be doing this. We're making part of it purposely factor into a perfect square trinomial. We're going to talk about that. This is one of them. I'll show you what that looks like so that we can make the square root method work. The second principle is this. I need you to understand that if something's an equation like we have here, if we start messing with one side by adding something to it, we have to undo that somewhere. And there's two choices, both are good. I'm going to show you in this video how to deal with completing the square on one side of your equation, because that will mimic more closely how you use completing the square later on in your math lives. So here's the principle. We all know that 7 equals 7. If I start adding or subtracting, mostly just adding, on one side of this equation, I have to balance it somewhere. And so here's what I want you to look at. If I start taking 7, and let's say I add 2, this is no longer a valid equation. It's not true. 7 plus 2 is not equal to 7. 7 plus 2 is 9. On the side we still have 7. I have to undo that somewhere. And so what I'm going to show you in this video is that in order to complete the square, in order to make factoring possible, we're going to be adding something to a piece of our equation. We're going to have to subtract on the same side to keep it equal. Now, a lot of textbooks are going to say, okay, I want you to add here, I want you to add here. That's perfectly fine. That is absolutely true. If you add 2 here and add 2 here, 9 would equal 9. I'm going to show you a different approach that will work better for you later. So instead of 7 plus 2 equals 7, even though this plus 2 kind of screwed us up, what if we did 7 plus 2 minus 2? Would that still equal 7? Well, yeah, the plus 2 and the minus 2, those are inverses. They're going to cancel out, if you will, and we would just get 7 equals 7 again. This is the principle I'm going to teach you in completing the square. And so here's the idea one last time before we start this stuff. We're going to take a look at how factoring works. We're going to make factoring work for something that's not actually factorable by adding a number to a piece of this equation. Then we'll have to undo that, because you can't just add to one side without undoing it somewhere. So I'm going to show you how that works, and let's take a look at this example in order to do that. So let's look at x squared minus 6x plus 9 equals 0. And we look at it, we've got everything on one side, we got it in order, we get the first term positive, and we say, number one, can we use the square root method in order to solve that? And we go, well, can I get that power 2? It's something squared on one side with no other x's and a constant on the other side. And the answer is no, that x messes us up. So the next thing we try is, can you factor it? You go, yeah, of course I can factor that. That's in order for some positive, looks pretty good, 3 terms. If I try to factor it, here's where we're going to start building this process. If we try to factor this, we'd use our diamond problem. We'd put our middle term, this -6, this b, up top, and we'd have a times c. 1 times 9 equals 9. Now, of course, because our a is 1, it's going to look like it's just 9. Now, here's something that I'm going to tell you we're going to do in just a minute. In just a minute, I'm going to say, now imagine something. Imagine we didn't have the 9. Imagine you still wanted to complete this, you still wanted to factor it as a perfect square trinomial, but you didn't have the 9. We're going to learn that if you can find these two numbers, that's the number that's actually missing. So I'm going to change this in just a minute, just watch for it. So if we went through this and said, okay, how to factor, we need two numbers to add -6, but at the same time multiply to +9, and we think in our heads, we know they're going to be the same sign, we know they both have to be negative, and they're both going to be -3. And if we continue, we know that whether we do a shortcut or whether we do factoring by grouping, we're going to get x minus 3 and x minus 3. And you go, wait a minute, that's the same factor twice. Exactly. So here's what I'm trying to show you here. I'm trying to show you that we're not going to be given the 9. We're going to be given something like, hey, missing the 9. And we still want to make this work so that when we put it together as x minus 3 squared, the square root method is still going to work for us. That's the whole principle of completing the square, is forcing something to factor so that the square root method is going to work. From here, yes, we take the square root on both sides. We get a plus and minus 0. We'd add the 3 and go, yeah, I can get that from here. I just get x equals 3. Hello. Yeah, exactly, because this was actually factorable. So here's the point. What we're going to do instead of having something that's already factorable, here's what it's going to look like. We're going to have, what if you didn't have the 9? What if this wasn't here? What if you wanted to complete this so that you forced it to factor? Well, if we ask that question, the answer would be, if I have this middle term of -6, I'm looking for this number, basically we're just going to kind of make up something that we have to add to it in order to make this thing factor like this. So you look at it and go, okay, well, how would I make this work? I'd make this work if both of these numbers are -3. You see, I still want this to be something that I have the same factor twice, something where the square root method would work when I combine my factors. So x minus 3 and x minus 3 need to make this x minus 3 squared. We have to have the same numbers here and here in order to get the same factor, in order to combine it to a power 2 so that the square root method will work, and that's exactly what completing the square does. It forces the square root method to work for us. The problem is, without this number, this doesn't work. So you go, wait. These numbers have to add to this one, right? Yeah, that's how we found them. We need them to be the same, correct? Well, of course, because we need this to happen so that we can combine them and get a power 2. But don't these numbers also have to multiply to here? Well, that's exactly how we did factor in the first place. We said these numbers have to add to this one, but at the same time, they have to multiply to this. So how do I find this number? Let's multiply them. Let's say, well, -3 times -3 is 9. 9 is the only number in the world that I can add to this and complete the square, complete the thing that we want to factor as a perfect square trinomial. So that 9 would get added right here. But we run into a situation. It's this situation right now. You see what I've done? I've added 9 to something that didn't have a 9. We'd have to undo that somewhere, and that's what we're going to focus on the rest of our examples. I'm going to walk you through this process. Right now, hopefully I've explained well enough the two major principles. Number one is we're finding a number that's forcing this to happen so that we can use the square root method. The second thing is, if I'm going to add something, I'm going to have to subtract something as well. Or I have to undo it, I would say. So we're going to practice that on this example, and we're starting right now. So let's say that we got this function, x squared plus 4x minus 3, and you need to find the zeros. So they say find the x-intercepts, or the roots, or whatever they call them, the zeros, x-intercepts, roots. And so the first thing you do is set the equal to 0. And then we run through all of our options on solving quadratic. So we think, well, is it on one side? Yeah, of course. Is it in order? That looks really good. Is the first term positive? Definitely. And then we'd say, well, we'd check. Does the square root method work? And the short answer is no, of course, because we have this x that we can't get at power 2 with all our x's inside and a constant on the other side. The next question is, can you factor? And you know what? You should try. you should try factoring for about 10 seconds. And if it's factorable, great. We should be able to do it in about 10, 20 seconds. And if that's not the case, if you can't factor this, you look at this and go, hey, there's nothing that adds to 4 and also multiplies to -3, then we've got to find another technique. Here's the 2 techniques we're going to choose from. They work all the time, but they're a little bit more intensive than like factoring and the square root method. They're completing the square, and then there's quadratic formula. Again, most of the time, guys, we're just going to go to quadratic formula because completing the squares, you're going to see on some of these examples, takes a really long time, and it's really hard to think of. But it is very valuable if you need it for later on in math. So I'm going to show you how that works, but just bear with me here that the quadratic formula is going to be a better choice for almost all of these. Just telling you right now. So let's see if we can make this work for us. So we're going to set this up, and we're going to set it up in a way that we're going to force factoring to happen. How in the world do we force factoring to happen? Here's the Leonard way of doing completing the square. Number one, I need you to think of this as this part's great, this part is the one that's screwing us up. Think about why that happens. If you were trying to factor this, the 4's not a problem. You could find numbers that multiply or that add to 4 very easily, but none that also multiply to -3. So we're going to take that -3 or that -3, we're going to hold it out for a little while. We're going to say this is the number that's screwing us up. So let's write x squared plus 4x. Don't lose this -3, but put it way over here. Put it way over there. Here's the thing that we're going to do. We're going to treat this piece exactly how we treated this piece without the 9. Remember how that 9 wasn't there. We're going to look at this. We're going to look at this. Treat this the same way. This is the thing that you want to factor. This is the thing that you're going to complete so that it can factor. So we're going to say, hey, if this were to factor, like if this were even possible, what would this part, ignore this, what would this part look like? This part would look like I have a 4. I wouldn't factor out the x. This is not a GCF thing. This is not what we're talking about. What we're talking about here is getting something where the square root method works. So you need 3 terms in order for this to have that perfect square trinomial look to it. So we're not doing a factoring by grouping. We're not factoring out the x here. We're finding a missing number that's going to make this possible. So again, we have this in order. We say factoring doesn't work. Correct. Take off the piece that's not working for you. Look at the first 2 terms. Make factoring work. How do we make factoring work? How do we make factoring work in such a way that we're going to have the same 2 factors? Well, if this is our middle term, after we find one, it's going to be our middle term. If that's our middle term, what 2 numbers add to 4? 2 numbers add to 4 that are the same number because we need to have that same factor. So we look at it and go, well, it's got to be 2 and 2. Those are the only numbers that are the same that add to 4. Again, why the same? Because if we can make these numbers the same, we're going to get x plus 2 times x plus 2. That shortcut or that grouping or whatever you want to do, if these numbers are the same, you are going to get the same factors here. There's only one problem. This does not factor like this right now. This is missing one number. And if we had that number, this would factor. And this would complete the square. It does. It completes the factoring for you. Well, what is this number that's missing? Well, do you remember? Like if this is the only 2 numbers that are the same that add to 4, this number comes from multiplying these 2 numbers. We're missing 4. So here's where that 4 comes in. That 4 says, if I were to add 4 here, this number that I would get, this multiplication, this is now factorable. So you've completed the one missing number right there that makes this factorable. So what we're looking at, we're saying that would be our middle term, put it here. Find 2 numbers that are the same that have to add to 4. Are you seeing that would have to be half of this number every time? It's always half of it. Because if you have 2 numbers that add up to something that are the same, it's always half the number you're trying to add to. Then, what would this be? This is always a multiplication of these 2 numbers, but that's always the number that's missing. So we're going to add that. It's always adding this number to it. But then we run into that 7 equals 7 with the 2 thing. We added 2, we had to subtract it somewhere. Here's where that happens. If you just arbitrarily add 4, you now no longer have the same equation that you started with. You've just changed your function. we have to subtract it, and we're going to subtract on the same side. So when we added 4, see, well, we got to take it away. This is the principle of, hey, if 7 equals 7, 7 plus 2 minus 2 is still equal to 7. We added something, so we undid it right next to it. That's what we're doing. We added 4 to make this factorable in such a way that it completes the square. We made it a perfect square. But in doing so, we added 4. We have to undo that 4 because if we add it and then subtract, it keeps our equation the same as it was. And then we're going to combine it and say, hey, that's minus 7. So we held out that minus 3. We subtracted 4. We also had a minus 3. That's a minus 7. Does that look familiar? That's exactly where the whole square root method came from. So all those problems we did a few videos ago where it was something squared, you get that square by itself, you take a square root on both sides, plus and minus, this is where it comes from. So we're making that happen by something that's not normally factorable. That's the whole idea. From here on out, I mean, we know that this is still equal to 0. And we can solve it. I might solve some of these for you. Probably not. I probably will do all of them. I always do. But if we solve this, we're going to add 7 to both sides. Oops. So x plus 2 squared equals 7. We take a square root. We know that when we take a square root, we have a plus and minus. So x plus 2 equals plus and minus square root of 7. We'd simplify the square root if we can. Here it's not simplifiable, so it's as simple as we can make it. We subtract 2, remembering where that 2 goes in front of our plus and minus. And this gives us 2 solutions. X equals negative 2 plus square root 7, and x equals negative 2 minus square root 7. That's it. And then you categorize it. So you think about that. Does that have any x-intercepts? And oh man, I hope it's making sense that if you have i's, you don't. You completely miss it. Complex solutions say we miss the x-axis. If we had one solution, it would have to be a real solution. We'd get it twice, and it would say our vertex is on the x-axis. Here, there's no i's. There's 2 distinct solutions. Those are 2 x-intercepts. If you want an approximation, you put in your calculator and you get about where this parabola, upward opening, crosses the x-axis at 2 times. That's got to make sense before we go any further. So we're taking something that's not factorable, stripping off this constant that's screwing us up anyway, figuring out what it's going to take to make it factorable. How? Think about if you wanted to factor a diamond problem, what would happen? These numbers would add to the middle one and multiply it to the last number. So if they'd have to be the same, so as to get the same factor twice, you'd basically just divide that by 2 every time. This number has to be the product of these 2. That is the number that you are adding. As soon as you add it, you will have something that's factorable because you just completed it. You just said what you needed to complete it, and then you added that in there. Therefore, this is factorable as something times itself. This is a square. We just have to undo the thing that we did. So if you add 4, you're going to subtract it. It's always going to be adding inside of a parentheses. Always, because you're multiplying a number times itself, aren't you? Number times itself is always positive. You're always adding here. And then we're going to be undoing whatever this is. I said undoing, not necessarily subtracting, because we can have some certain special circumstances. So we'll talk about that in a bit. Then we combine the number we didn't really want in the first place with the number that's keeping this thing the same function. And we would get exactly the same function, just written in a different form, something where the square root method will work. And if you wanted to check your work, you could distribute this and subtract 7, and you're going to get exactly that. That's where I need you to be right now. All right, so let's keep on going. Now we got this g of x squared minus 3x plus 1. We're thinking it's a quadratic. It's an upward opening parabola. It's probably going to have some x-intercepts, but if we run into any i's, well, then of course we wouldn't. We'd have some imaginary solutions. So when we're asked to solve for x-intercepts here, the first thing we're going to do, like every time we have a quadratic and you're asked that question, is we're going to set this thing equal to 0. And we're going to say, what's the method? What should we go through? The first thing we should try is the square root method. It is the fastest and easiest, but it only works if you have something raised to the second power. with all containing all your x's. And this is going to screw us up. If we solve for x squared, we'd have an x on the other side of the equation. It says the square root method will not work right now. The next thing we would try to do is we try to factor this. You take this over here, you'd say, all right, here's my -3, here's my 1. I'm trying to look for any numbers that add to -3 and multiply to 1. And you go, you can't. You can't. There's no numbers that add to -3 and multiply to +1. That's the whole point. This thing is not factorable. Now, what is the problem here? The problem is that this 1 screws us up. We can't really change the -3, but we can hold off the 1. So here's the whole point of completing the square. We love the square root method. It's really nice, but it doesn't work right now. This won't factor. So what we're going to do is we're going to kind of combine the ideas. We're going to make this factor so that the square root method will work. How we're going to do it is we're going to say this 1 that's screwing us up, we're going to hold that off for a minute. We're going to hold that way over here. We're not losing it. Notice I've written it down. I just don't want to consider it's here because it's not factorable. We're going to find something that is. So here's how we find something that's factorable. It's not super fun with fractions, but I need you to think back to the last example. In our last example, when we didn't have this 4, we thought about it and we said, all right, what we want is we want to end with something that has the same factor twice. Why? Because you still want the square root method. So we want these numbers to be half of this one. Something plus itself equals what we have been given. So we look at the 4 and say, I want 2 numbers that add to 4 that are the same number. It's going to be half of 4. I want 2 numbers that add to -3 that are the same number. You go, that's not easy. It's like 1.5, like -1.5. Yes, it is. Half of 3 is 1.5, or 3 halves. And so half of -3 is -3 halves. We need the same number twice. In order for this to have the same factor twice to be written as a perfect square, we need the same number twice. That's imperative. So we have that and go, well, okay, that doesn't look nice, but let's think about it. If we wanted to add a number to make this thing factor, it would have to be a number that these two things multiply to. Remember how this factoring works. We add to this one, we multiply that one. So when we looked at our 2's, we said we want these numbers to be the same. Okay, they're both 2. We need a number that when I write it here, it's going to make this factor. We know that these two numbers have to multiply to this number, whatever it is. 2 times 2 is 4. You're creating the number that you're adding to this equation so that you can make it factor. That's what we're doing. So we're looking here, we're saying I need my 2 numbers that I'm finding to both be the same. They both got to add a -3. It's got to be half of that. But I've got to add to this expression right here on the side of my equation. I've got to add to it something that makes my factoring work. In order to make factoring work, this number has to be the product of these. That's, let's see, negative times negative is a positive. Do you see where we're always adding? 3 times 3 is 9, 2 times 2 is 4. That'd be positive 9/4. If I add that, this right here is what we just created here. It says this right here is missing the number to make it factor. What number? Find the number. If I add that in, that now creates something that is factorable. We just created something that will give us a perfect square trinomial. You don't have to worry about factoring this again, because you made it in such a way that it's already factorable. Look what you did. You said, I want to hold off my 1. Sorry, it should be a plus. I want to hold off my +1. I want this thing without my +1 to be factorable. And if that were to happen, my middle term goes here. I need my 2 numbers I'm finding to be the same in order to get a completing the square or a perfect square trinomial. I need this number to be the product of these. So if I multiply this, that's the number that's missing. It's already factored. You already found what this thing is going to factor it as. In fact, you found the number to make this happen. So this would be x minus 3 halves. We know that. And another x minus 3 halves, or x minus 3 halves squared. There's one thing that we have to do to make this perfect. You just added 9/4 here. We need to undo the 9/4 that you added. So we held off the 1. We looked at the x squared minus 3 and said, I really want that to factor. What's missing? Let's figure it out. What's missing is that would be a -3. We find numbers that are the same to add up to that. We multiply them to find the missing number. It's always a constant. Find the missing number that's going to make this factoring complete as a perfect square, completed square. But when you add something, you have to undo that. You can't just start adding random numbers in there. So we add 9/4, we subtract 9/4, and you combine these two pieces. So when we combine -9/4 and 1, let's see, -9/4 plus 4/4 is -5/4. So -5/4 equals 0. And now we have something that, even though it's really ugly, you can use a square root method on. It has a power 2 with all of our x's in it. We can get a constant on one side. If we take a square root on both sides, with a plus and minus, we'll simplify the right-hand side. So 5/4 will have the square root of 5 over 2, because square root of 4 is 2. So I'm going to move over here. So x minus 3/2, square root and power 2 are gone. That's fantastic. We'll get plus and minus square root 5 over 2. Again, the square root of 4 is 2. If we add 3/2, we really do get two solutions. Think about it. Are they x-intercepts or are they imaginary? Does this cross the x-axis twice? Yes, it does. There are no i's. There's no imaginary complex zeros. So we have x equals. There's two ways to write it. You can leave it as a fraction plus another fraction, or because these have a common denominator, you can write this as, no common denominator, 3 plus square root 5 over 2. And 3 minus square root of 5 over 2. If you've ever had any exposure to the quadratic formula, that might look very, very familiar to you. Why? I'm going to kind of ruin the surprise in the next video, but I'm going to prove the quadratic formula to you. And you know how we're going to do it? We're going to do it with completing the square. I'm going to do this exact same thing, but instead of having actual a is 1, b is 4, c is -3, we're going to have a, b, and c being a, b, and c. And we're gonna do completing the square, and we're gonna get the quadratic formula from it, which is why these answers can sometimes look very, very, very similar. So I'm hoping that makes sense. I'm hoping you're seeing the reason why completing the square works. Most of the time, what I've seen teachers do, or textbooks do really, is they say, okay, it's a process. What you're gonna do, divide this number by 2, goes here, multiply the numbers together, you get this, and then put this on the other side to keep it equal. I get that. It does work, but when you get to later levels of math, people completely miss this. You go, what is it? What's that for? This adding 4, subtracting 4, this adding 9/4, subtracting 9/4. If you add something to an equation, you can subtract it on the same side, and it's going to keep that equation the same as it was, and that's what we're doing. The other thing that I need you to keep in mind is that when you're setting up your factoring, you are forcing factoring where it shouldn't, where it doesn't already. So you're forcing this to factor by having the same number twice. It's got to always be the same. You're always adding, you're always undoing whatever you've done on the same side of your equation, and then we're making it so that the square root method actually works and solving it. So let's try one more, and then we'll kind of make it harder. All right, let's take a look at the last one before we start dealing with some funky fractions. There's one other principle I haven't explained yet that I need to explain in this problem. So I'm going to walk you through it. I'm going to tell you exactly what we've done already, and I'll talk about how our A needs to be 1. And the reason why that is as we go through. So you're faced with this problem and it says, hey, you gotta complete the square. You gotta prove to me that you can complete the square. Or you're later on in math, like, I don't know, calculus 2, and you have to find some sort of a completing the square to make the problem happen. So the first thing we're gonna do is we're gonna set this equal to 0, because we know that anytime we wanna find x-intercepts, roots, zeros, whatever, we're gonna set our function equal to 0. So we're gonna get 5x squared minus 10x plus 2 equal to 0. And you know what? We're going to try the square root method first. Is there a way to get a power 2 with all your x's inside of it and everything else that doesn't involve x's on the other side? And the answer is no. Again, this x right here says that the square root method will not work the way it is right now. So we try factoring. All right, well, let's try to factor. If we try to factor, then we would have negative 10 and we would have 10. Because 5 times 2 would give us 10. You say, there's no way that's happening. There's nothing that adds negative 10 and multiplies to positive 10. We don't have any numbers that do that. So we're going to start setting up completing the square. Now we're going to do that by taking this 5x squared minus 10x plus 2. Don't forget that plus 2. Plus 2 equals 0. It's the same exact equation. We're just going to set this up so that we can force this thing to factor as a perfect square. There is one drawback. The only drawback is that that 5 is going to really hurt because it's a lot harder to complete that when you can't use this nice direct shortcut. Do you remember the direct shortcut? The direct shortcut said, if I divide this by 1, I get 1x plus 2, 1x plus 2. Same thing down here. Divide this by an a of 1. 1x minus 3 halves, 1x minus 3 halves. That actually worked for us, but it's fairly difficult to do that if we have to multiply to 5 alongside of our c that we're finding. So if we have to find this number and also make it multiply to 5 times that number, we're going to have an issue. And so what happens is that completing the square is best done if your a is 1. Because we can start using these nice shortcuts that I taught you in the previous videos. So what we're going to do is we're going to factor out whatever this a is. So our a here is 5. Do not factor it from this number. You don't have to. So we're looking at saying it's an order one side, first term positive factor doesn't work, short method doesn't work. We're pulling off our x terms because we're going to make this factor. We're holding back our plus 2, our constant, and then we're going to force this to factor, but we're first going to make sure that our a is 1 that we're dealing with. So we're going to factor out a 5. We're going to get x squared minus 2x. What now? This piece is what you want to factor. I don't care about the 5 right now. I just care about this. Do you see how much easier that makes this? Like if you have that 5 there, it's fairly difficult to figure out what you need to factor to make it a perfect square in that. Like it's not easy. But if you have this, well, it's not as easy. If you have this without the 5, this is now pretty nice. All we're going to do is we're going to take and mess my board up. That's what we're going to do. We're going to force this to factor. We're going to force this to factor with a negative 2. We're going to say, hey, you know what? If I want this to factor as something times itself, I need 2 numbers that are the same. So we think, what numbers are the same that add to negative 2? It's always got to be half of this number. Half of 4 is 2. Half of negative 3 is negative 3 halves. Half of negative 2 is negative 1 and negative 1. Those are the only 2 numbers that are the same that add to negative 2. We also know that if we're going to complete this square, this is missing a number. That number has to be the product of these 2. So we go, well, that's 1. It's always positive. If you multiply 2 numbers that are the same, you will always get a positive. You're always going to be adding it in here. So when we look at that, we go, all right, that's got to be plus 1. So if we add 1, what we've just done is we've forced this expression to follow the pattern that we needed it to follow, that we created, so that it will be factorable. You don't have to worry about factoring this again. You've already done it. You said these 2 numbers will add to my middle one. These 2 numbers will multiply to my last one. In fact, you gave it the last number so that it would multiply. So I know for a fact this is going to factor as x, there we go, x minus 1 squared. That's going to be the case. Now, man, if you don't miss this. This is the one thing you gotta make sure that you don't miss. Otherwise, you'll be really frustrated. What number did you add? Well, it looks like you added 1. But notice where that 1 is. This is the hardest thing for students to grasp. Notice where that 1 is. You added 1, didn't you? But you added it in an expression, a parenthetical expression, that's being multiplied times 5. So wait a minute. If you were to distribute this, you would get x squared minus 10x. This actually counts for minus 10x because of that 5. And you would get plus 5. So in adding that 1 inside of a parentheses, you have to count on the distribution factor. So when you distribute this factor, that adding 1 actually turns into an adding 5. So how I always teach my students to do this, I say, hey, distribute this. What do you get when you distribute this? You get plus 5. Undo that. So if this says 5 times positive 1 is positive 5, we need to undo the adding 5. You need to subtract 5, not 1. If you subtracted just 1, and then you distribute all this stuff and combine it, it will not be what you started with. It's not going to be that. Now it will. If you want to try this right now, 5x squared minus 10x plus 5 minus 5. Oh wait, plus 5 minus 5 is 0. Plus 2. That's exactly what we had. It's a minus 5 that's necessary in order to make this factoring consistent with what we had originally. So we looked at it, we said it's in order, but the square root method of factoring does not work. Let's make it so that the factoring is easy and it works. Let's factor out the 5. Now we have something where we can complete the square. We take a look at our middle term on this 3-term polynomial that we're building right now. We say I need these numbers to be the same. Great, divided by 2. We say that the number I need to add has to be the product of those. Why? Because your a is 1 now. If your a is 1, it's really easy to understand that these two numbers multiply to your a times c. But 1 times whatever number I'm getting is still my c, and that's what I'm adding. When I add that, be very careful. If you have to distribute, you need to undo the distribution, not just the number, undo the distribution. Now we see that this is, okay, I've got an x minus 1 squared. I would still have my 5 as a coefficient. I would now have a minus 3 equals 0. I'm combining these two, minus 5 and minus 2 is minus 3. From there, man, we just solved it. We solved it the rest of the way. If you want to, and this is just the square root method, if you want to do it on your own, you add 3, divide by 5 first. We take a square root on both sides. Depending on whether your teacher needs you to rationalize the denominator or not, you might have to rationalize the denominator there. So square root of 3 over square root of 5, multiply by root 5 over 5, you can get square root of 15 over 5 if you do that, and then we would subtract 1. So negative 1 plus or minus square root of 3/5 or negative 1 plus or minus square root of 15 over 5. Whatever one of those ways you need to do. The main concept I'm really concerned about is getting you down to here. I've taught you the square root method already. We're just isolating the square root, taking a square root on both sides with a plus and minus and getting 2 solutions. In this case, 2 real solutions. There are no negatives inside square root, so we don't have any i's. Now, with that in mind, let me talk about that. What if this had happened to be a don't change your work. But what if this had been a plus? Well, then when I subtracted it, I would get a negative. And I would have a negative here, and it would give me an I right out in front of that square root. That right there would tell me that I have no x-intercepts. These would be 2 imaginary solutions. That's important. I need you to understand it. I think that's about it for right now. What we're going to do in just a minute is we're going to come back and we're going to have at least 2 problems that are a little more challenging because they start off with fractions, and I need to show you what to do with that. All right, so let's get after it. So we have 3 more problems to do. These ones are the toughest ones I could find or make up. Made up that one to see if we could handle it the way it is without changing signs. So what to do with when you have to factor out negatives there. So we're going to take a look and say, hey, you know what? On all these problems, I'm going to ask you to find x-intercepts or find zeros or roots, complex or not. And so we're going to take all these problems, we're going to say set them equal to 0. Put them in order, one side, first term positive, and see if the square root method will work. If it does, great. If not, try to factor it. If not, well, then we'd probably go to quadratic formula, but I'm going to show you completing the square so that you can do it. So let's set this equal to 0. And when we take a look at it, man, we really like square root method of work, but it's not going to happen. That x messes us up. And factoring, no, it's not going to factor because there's nothing that we can find that adds 2/3 and multiplies to 1 times negative 1/3. And so what we're going to do is we're going to strip off that constant, and we're going to have this as x squared plus 2/3 x. We're going to have this minus 1/3 over here equals 0. You see, the constant is what is messing up our factoring. We're going to find a different constant so that the factoring works. So we're going to take a look at this part right here. We're going to find what number we can add to this to make factoring work for us, but make it work in a very specific way. We want it to work so that we have this perfect square. The same factor twice, we raise to the power 2 so that square root method will actually work. So we take a look and say this 2/3 right here is what I want to add to. But if we're going to have the same factor twice, these numbers need to be the same. Now, what in the world are they going to be if they're the same number that adds to 2/3? Well, it's going to be half of 2/3. Here's how to find half of a fraction. Either divide the numerator by 2, if that works evenly, or multiply the denominator by 2, if you can't divide the numerator. So in this case, we look at the numerator and say, hey, 2 divided by 2 is 1. Half of 2/3 is 1/3. Or 2 times 3, our denominator is 6. 2/6 is 1/3. So either way you go, you're going to get this 1/3. Of course, 1/3 is half of 2/3. They're both positive because you are actually adding to positive 2/3. So we found the number that's going to make this factor as the same factor twice so that we can put it together as a perfect square. That's perfect. What we're missing is the number that we need to add here in order to make this factoring work. So what we know about that number, we know that these two values that we found that add to your middle number also have to multiply to your a, which is 1, times c, the number we're looking for. We're looking for the c. Because we've made certain that our a is 1, so that this factors very nicely for us, when we multiply these two numbers, you get 1/9. If this number is always a times c, and your a is always 1 for this complete the square, then 1 times this number is your c. Well, 1 times 1/9 is 1/9. This is the number that we're going to add to this part of our equation to make the factoring possible. Do you see it? I hope you're seeing it. That when I add that, it is now completing this process. We knew what we had to have, we just were missing it. You're adding it so that this process that you just created works. So this one's our middle number, we have to have the same number twice, just divide by 2. Multiply here, this is the number that's missing to make the factoring possible the way I want it. So we know that this is going to factor as x plus 1/3 and x plus 1/3, or x plus 1/3 squared. I hope you're seeing what's missing right now on the board. It's got to be there in your head that we just added something and we never compensated for that. So when we added 1/9, we're going to have to distribute. So 1 times 1/9. Okay, we've added 1/9. Let's subtract 1/9. On the left-hand side over here, well, we know that this expression is factorable as x plus 1/3 squared. We just showed that. That's right here. It's x plus 1/3 times x plus 1/3. Our a is 1. The shortcut works very nicely for us. Let's see. Minus 1/9 minus 3/9 is minus 4/9. So this would be 3/9, 1/9, 4/9. If we set, man, this is beautiful. It's a square root method is going to work perfectly if we add 4/9 to both sides. If we take a square root on both sides with a plus and minus, then x plus 1/3 equals plus or minus 2/3. And if we subtract 1/3, we get negative 1/3 plus or minus 2/3. And we know that we're going to get two solutions out of here. There's two real solutions. So x equals negative 1/3 plus 2/3, negative 1/3 minus 2/3. Well, this x is going to be 1/3. And this x value is going to be, let's see, negative 1/3 minus 2/3 is negative 3/3, that's negative 1. So we have two x-intercepts. We have one at positive 1/3 and one at negative 1 on the x-axis. This is the upper opening parabola. Now, I did that because sometimes you're going to listen very carefully, hear the words behind what I'm saying here. Would I actually do this for solving x-intercepts? And the answer is no. No, I wouldn't. I'm going to show you that right now. But the second part of it is it still valuable to learn what we've done? Yes, because later you may actually have to do this when you're not asked to solve for x-intercepts. So how would we do it? What would we do instead? Man, every time you have an equation, wouldn't you get rid of fractions? Wouldn't you look at this and say, hey, my LCD is 3. Let's multiply everything, both sides, times 3. That's going to give us 3x squared plus 2x minus 1 equals 0. 0 times 3 is still 0. Is that going to factor with 2 and negative 3? Yeah, you'd get 1. Sorry, I had that backwards. 3 and negative 1. This adds a 2, this multiplies a 3. If you divide by your a, which is 3 here, we'd get positive 1 over 1. We get negative 1/3. This says, your denominator says you'd have 1x plus 1. This says you'd have 3x's minus 1 equals 0. If you set them equal to 0, x plus 1 would equal 0, 3x minus 1 would equal 0, x would equal negative 1, and x would equal positive 1/3. It's the same exact thing. So which way is easier? Probably the factoring's easier. Probably the factoring's easier. But again, it's valuable to understand, and especially if your teacher shouldn't making you show this stuff, you gotta do completing the square with a fraction. Now you know how to do that. I hope that I've made it easier for you to understand why you're doing what you're doing, because sometimes it just becomes a process and you go, okay, I just divide this by 2 and square it, but I have no idea why. And then I subtract this random number because told me to. This is the reason why. I hope you're seeing that you were just making the factor I taught you earlier possible. Okay, last two, we're going to kind of whip through these as fast as we really can. So I'm going to show you the process, especially on that one. Again, I hope you understand that really what I'm going to intend to do is if you can't factor something, get rid of your fractions first. And if you still can't factor something, pretty much we're doing quadratic formula. Here we're kind of just practicing. So f of x equals 3x squared plus x minus 1/2. We're looking for zeros, x-intercepts, roots. So we're going to do 3x squared plus x minus 1/2 equals 0. We got to set equals 0. It's on one side in order first term positive. Looks pretty good. We say, can the square root method work the way it is right now? No, that x messes it up. Can we factor the way it is right now? No, not really with fractions. Could you get rid of your fractions? Yes. Yes, you could. If you multiplied both sides by 2, 2 here and 2 over there, we'd get, I'll show you. We'd get 6x squared plus 2x minus 1 equals 0 still. Now, is the factoring going to work? We'd have a 2 here, we'd have a negative 6 here. Can you think of any numbers that multiply to negative 6 and add to 2? I'm not seeing it right now. I can't think of anything that adds to negative 6 and multiplies, adds to 2 and multiplies negative 6. So that's not working for us. Factoring wouldn't work like it did in the previous problem. So what would you do now? Listen, please get this. If you're just looking for x-intercepts, you probably would not complete the square here. What you'd probably do is get rid of your fractions and do the quadratic formula, which we have not talked about. Do the quadratic formula from right here. So I hope you paid attention on that one. In like real life situation, you're rarely going to complete the square on this to find x-intercepts. It just takes too long, but the quadratic formula would be quicker. So that's what we would do in order to practice the square root method. Or if you have this function, and you have to complete the square on the function, which does happen from time to time, and you can't change much about it, well then this is great. This is the technique I'm showing you. This is the reason why I'm not working on both sides of my equation. You'll see that most textbooks will add to one side and add to the other side to keep it stable, if you will, balance-wise, keep it equal. I'm not doing that because I want you to learn how to deal with one side, deal with the function by itself without having to compensate with another side of an equation that doesn't exist. So that's why I'm showing this way. All right, we're taking a look at it. Let's do the completing the square thing. We're going to take our 3x squared plus x. We're going to take this minus 1/2. and the equals 0, we're going to factor out a 3 from just here because we want the square root method to work by forcing this to factor, but we also know that our a really has to be 1 in order for us to use that shortcut very well. So we're going to factor out 3. We know this is 3x squared plus x. We have a missing number. This is what we're finding. This is what we're looking at our factoring for and saying, hey, here's a 1/3. Here's a 1/3. I need to find half of that number. I need to find the number that I can add to itself to give me 1/3. Well, it's going to be half of 1/3. How do you find half of 1/3? You either divide the numerator or you multiply the denominator. So I can't divide the numerator easily, but I can multiply the denominator. So 3 times 2 is 6. Divide the numerator by 2 or multiply the denominator by 2. This is going to be 1/6 and 1/6. 1/6 plus 1/6 is 2/6. Sixths. That's going to be 1/3. That right there says what this is going to factor as. So this is going to be x plus 1/6 and x plus 1/6 because our a is 1 right now. This is what we're dealing with. Now, the number that's missing to make this happen is whatever is here. We know that these numbers would have to multiply to our a times c. Since a is 1, this is just going to be our c. 1 times c is c. So since a is 1, whatever we get for our multiplication is going to go right there. So let's see, 1/6 times 1/6 is 1/36. We're going to add 1/36. But we're also going to have to undo that. Now think carefully, what are we undoing here? Are we going to undo adding 1/36? No. Because we have a 3 here, pretend to distribute. 3 times 1/36 is, well, let's see, 3/36. That's 1/12. This is, you basically added 1/12. 3 times 1/36 is 1/12. That's what you added. That's what we're going to subtract. Minus 1/12. This is already set up for factoring. We already completed it. So we know that all that number did was say, oh, now this works. Because if you tried to factor this, look at it. You'd have 1/3 here. You'd have 1/36. You find two numbers, add to 1/3 and multiply to 1/36. That's 1/6 and 1/6. This is now factorable as x plus 1/6 squared. We have a 3 out front. Minus, let's see, minus 1/12 minus 6/12 is minus 7/12. We're going to add that 7/12. We're going to add that 7/12. The next thing we do is before you take a square root here, you have to divide that by 3. So when we do divide by 3, we're going to get x plus 1/6 squared equals, if you divide this by 3, dividing a fraction by 3 is the same thing as multiplying by 1/3. Do you remember that? So we can multiply by the reciprocal. So if you ever divide a fraction by a whole number, just multiply the denominator by that whole number. So if I divide 7/12 by 3, I'm really taking 3 times 12. 36, that'd be 7/36. Now we're able to take a square root. Now we can have a plus and minus. We can simplify and get this x plus 1/6 equals plus or minus the square root of 7/6. Looks pretty familiar with something we did earlier. And then we subtract 1/6. So negative 1/6 plus or minus the square root of 7/6. I showed you a couple ways you can write that. The main thing is I need you to understand there's two solutions here. There are two x-intercepts. They're not complex. This is where this parabola is upward opening, somewhat narrow, crosses the x-axis twice. This is the way, man, in my opinion, the best way to complete the square without just using an arbitrary technique is thinking about what it is you're doing. What you're doing is you're factoring. You're forcing this thing to factor by finding the missing constant that creates this perfect square factorization that you already have down. All right, the last one, and then we're gonna be done. Okay, I'm gonna change it up just a bit. I'm not gonna go through this last problem as solving it for an x-intercept. I'm going to go through this problem like what you would see later on if you're forced to complete the square within a function. So I'm going to leave the h of x here. I'm going to validate the technique I'm using because like I said, most times you'd add the 1/12 on the other side of the equation. I'm going to show you that the reason why I'm doing that in this example is because sometimes you got to do this without solving for 0. So let's leave the h of x up there and let's complete the square the way that it is. So what are we going to do? Well, we're going to hold out that negative 2x squared plus 5x. We'll put this minus 7 way over there. Not forgetting about it, but we're just kind of losing it for a second. After that, we're going to factor so that our a is 1, so that our shortcut works very well. We understand that what we'd be getting multiplies to exactly the c, 1 times c, so we find that missing constant. Otherwise, it becomes very difficult. So we're going to factor out negative 2. If we factor out negative 2, we get x squared, we get minus 5 halves. 5 divided by negative 2 is minus 5 halves x. We're going to be finding a missing number here. One thing I want to just comment on, if you did have this set equal to 0, the first thing you do, change all your signs. You change all your signs and see if it's factorable. With negative 5 and positive 14, you just change your signs. So add negative 2, subtract 5x, add 7. And so if you had 0 equals, much like getting rid of the fractions first, remember that? Much like that, you'd make sure everything's on one side in order, first term positive, and that is already a whole lot easier to deal with. You'd see if factoring works. If it does, great. If it doesn't, well, then you would go ahead and you do quadratic formula. Right now I'm completing this with, and I think this actually is factorable. No, it's not. But you would at least try that. And then you do quadratic formula probably. Okay, so here we are. We know that if that was a 0, we just change our signs and go for it, probably quadratic formula. But now, since we're completing the square, we're going to go ahead. We're going to have our b term, negative 5 halves. We're understanding that I need these two numbers to add to that and be the same, which means we're going to have half of this number. That's the only way you find two numbers are the same that add to something is find half. So negative 5 halves divided by 2. Either divide the numerator or multiply the denominator by 2. That's going to be negative 5 fourths and negative 5 fourths. That actually does add to negative 5 halves. Negative 10 fourths is negative 5 halves. And now we find the number that's missing. You see, this isn't here. There's no c right now. We're going to find what this takes to make this factorable, and then we're going to add it in there to force this to happen. So negative 5 fourths times negative 5 fourths is positive 25 sixteenths. That is what we're missing. So we're going to take this, we're going to add that. 25 sixteenths. This is now factorable according to what you found. The problem is you just added 25 sixteenths. Here's the issue. I hope that you're seeing it. Did you really add? Be very careful. Because this negative 2 is going to distribute by adding 25 sixteenths, you really, watch, negative 2 times 25 sixteenths is negative 25 eighths. 2, 16, cross out, you get an 8. Negative 25 eighths. That is what you actually subtracted. I know it's a little weird, but if you were to distribute this, you'd have negative 2x squared, you'd have plus 5x, and you would have minus 2 times 25 sixteenths. This would subtract 25 eighths. You need to add that. So we're distributing and then undoing that distribution. By distributing, you're finding out that you really subtracted 25 eighths. You are adding that back. You're undoing the distribution here. We kind of did the same thing with our 1. You said, hey, 1 times 1/9 is 1/9. You need to subtract the adding of 1/9. 3 times 36 is, whatever that was, 1/12. You're undoing the 1/12. Negative 2 times 25/16 is negative 25/8. Okay, we're adding 25/8. You're undoing that distribution. Then we're going to combine our like terms, which are constants over here. We're going to factor as x minus, it's already factored. You already have it, x minus 5/4 squared. We know that we had a negative 2. And then we're, oh man, let's see. 25/8 minus 7 minus 31/8. And that looks really nasty, but if you had to complete the square, our function written as a completed square is pretty darn nasty. If you had to set that equal to 0, you could use that to now find whatever your x-intercepts would be. Will there be any? So if we added, yeah, there'd still be some x-intercepts there. They're going to be kind of ugly, but you could certainly find them. So I hope this makes sense. I hope at least what I've done is illustrate the way that completing the square works. Not that you use it all the time. So if you caught anything on this lesson, it's this. Number 1, completing the square is taking factor and making it happen. Number 2, when it gets hard like this, mostly for finding x-intercepts, we're going to be using quadratic formula. That's the way that we do it. We look at this and say, can you use the square root method? If not, try factoring. If not, go to quadratic formula. Completing the square, it's rare that we do it to find x-intercepts. I taught it to you so that it wouldn't be the scary thing. And because you do use it as you go later on in mathematics. So I hope I've done a good job of explaining that to you. Hope you guys are having a wonderful day. And next video, I'm going to show you a proof of what the quadratic formula comes from by completing the square.